for different accelerators, or it's just
Yeah,
one
low
sample
investment.
kind of thing?
Yeah, of course. Yeah, I mean, yeah, so what one would do, I think, is you basically, the other two pages would graph or round. And then,
All right. Nicole, can you hear me?
Yeah, sorry, I can hear you.
Okay, great.
It's a bit faint, but yeah.
All right. All right, everyone. So we're gonna get started. So yeah, everyone. All right. So today was the first day of our quantum theory seminar for this semester. It's gonna be Fridays, 3:30 p.m. And we have a nice lineup of speakers. Our first speaker we're happy to have today is Nicole Ticea from Stanford. She is a grad student working with Shrey Raghu and Tritep Devakul. Currently, she's on a one-year leave from her PhD to Google Quantum AI in Santa Barbara. And today she's going to tell us about the stability of quasiperiodic superconductors. So thank you, Nicole.
Great. Thanks so much for the intro. And thank you for inviting me here. It's a pleasure. So like Omri said, my name is Nicole, and I'm here to talk to you about my recent publication on superconductivity in quasiperiodic systems. So back in undergrad, it was tradition to start each group meeting with a piece of art that's somehow inspired or related to your work. And I remember like back then I was sort of drawing like a lot of like tenuous connections between science and art. But luckily today, the link is actually very easy to make. So the picture I'm showing you right here is a photograph of the Darb-e-Iman shrine in Iran. And parts of these mosaics are tiled using a set of tiles which are known as the Giri tiles up here in like the upper left-hand corner. And this is sort of like, it's a set of tiles that can be used to produce a quasi-periodic pattern. And I guess I couldn't resist one more interesting like tidbit of information related to quasicrystals, is that the first man-made quasicrystal ever produced was generated during the Trinity bomb tests. And actually, this wasn't known until 2021 when samples were studied using diffraction. And here in this bottom right-hand corner, you can see that this crystal has a five-fold rotational symmetry, which is sort of conventionally forbidden in traditional crystals. And this is because in a regular crystal, you would have a unit cell. And specifically, a crystal with five-fold rotational symmetry would have a rhombohedron unit cell. But it turns out that you can't actually tile the 2D plane using rhombohedrons, which is why this sort of symmetry is like traditionally forbidden in regular crystals. But because a quasicrystal doesn't have a unit cell, you can sort of get around this problem entirely. And that's how you get these really nice diffraction patterns. Okay, cool. So what exactly is a quasicrystal? It's a very interesting system to study because it sort of blurs the line between perfectly periodic crystals, which is what we're familiar with in condensed matter, and amorphous structures. So unlike in a regular crystal where the atoms are arranged in a repeating pattern, the quasicrystal will break translational symmetry. But the important thing to keep in mind is that the quasi-periodic potential is still very highly structured in momentum space. And here on the right, I showed the diffraction pattern of sort of an ideal infinite quasicrystal, and you see that it's characterized by a self-similar arrangement of Bragg peaks, which are densely tiled throughout reciprocal space. So because quasicrystals are not ordered, one might feel compelled to call them disordered. And indeed, translational symmetry is broken, momentum's no longer a good quantum number, and as a result, you might expect to see localization of your single particle eigenstates. This is what happens, and I guess like to understand why, it might be helpful to think about starting just off with like a tight binding model with no hopping, and then you slowly turn on the hopping as a perturbation. And what happens is that if the differences in potential between nearby sites are large compared to the hopping, this will end up detuning most intersite resonances, and this will suppress your hopping. And traditionally people, think about these detunings as being due to randomness, but they can also equally validly be produced deterministically without randomness, such as with a quasi-periodic potential. So one might ask, what is the right way to think about quasi-periodicity? One perspective that you might want to take is that a quasi-crystal is just like quote unquote random enough to localize your single particle states. And as a result, you might expect to see the same phenomenology as you have in the presence of random impurities. If this is indeed true, then one would expect to see most known results on disordered systems replicated in the quasi-periodic case as well. And what really motivated us in pursuing the study was Anderson's theorem for disordered superconductors and asking whether an analog or a generalization thereof also applies to quasi-periodic systems. So what is Anderson's theorem? We'll start off by describing exactly what it is. And it's really just a statement about S-wave superconductors with implications for non-S-wave superconductors, which we'll get into in a moment. But here we're just going to consider the S-wave case. So I've written down the expression for the gap. And what I want to do is rewrite this expression in the basis of the single particle eigenstates, which are solved for in the presence of disorder. And they're just labeled by these indices alpha and beta. And in general, one might expect that delta of R will be a very complicated function of position. But in the presence of weak disorder, the eigenstates are still extended in real space or localized in momentum space. And at any particular location, delta will actually contain a sum over a very large number of nearly random contributions from the different eigenstates. And in this situation, Anderson argued that delta of R really sums up to a nearly constant value all throughout space. So when disorder is weak, we can replace delta of R by its spatial average, which I just call delta. And then finally, the last step in this sort of heuristic derivation is to apply the orthogonality relationship of the eigenstates to arrive at a final expression for the gap, which is non-zero in this S-wave case. So next, I'm just going to provide a very heuristic, hand-wavy explanation for the implications of Anderson's theorem to the case of non-S-wave superconductors. A real derivation is truly much more involved, and I'm happy to talk about it after the talk. But yeah, so first let's consider the S-wave case, which I just described. So you can sort of imagine that I pick a pair of particles up out of the condensate, and then I scatter them by some disorder wave vector Q. Because I have S-wave symmetry, the order parameter doesn't actually depend on momentum at all. So the gap is sort of unaffected by this scattering process. But conversely, if I had a D-wave superconductor, you can sort of imagine the same thing. You take two particles out of your condensate and then you scatter them. And because your gap function is sign changing across the Brillouin zone, you'll end up picking up a phase due to the scattering process. And this phase that you've picked up will interfere destructively with the phase of the original Cooper pair. And as a result, your superconducting gap, when you perform this average, will go to zero. So let's summarize this information just pictorially with a phase diagram. So what Anderson's theorem tells us is that conventional or S-wave superconductivity will not be suppressed for a finite disorder strength. And it's only really when the localization length is the most important length on the problem, so like in the insulating regime, that we really start to see like suppression of superconductivity. And conversely, unconventional superconductivity such as P or D wave will be killed by even small amounts of disorder. And again, this is because the gap function for an unconventional superconductor carries momentum dependence and will, as a result, vanish upon performing this spatial averaging procedure. And this is really the content of Anderson's theorem. So one might naturally wonder, what, if any, is the analog of Anderson's theorem in a quasi-periodic system? As I'll motivate in a few minutes, quasi-periodic systems display truly remarkable transport properties that will eventually play a really important role in understanding what kinds of superconductivity these systems can support. Okay, so let's be a bit more specific about the system that we're going to study today. A paradigmatic model for studying quasiperiodicity is called the Aubrey-Andre model, and here we're going to look at it in 3 dimensions. We have a single particle part H naught and a spatially modulated part HQP. This potential is spatially incommensurate with the underlying lattice, which is what makes this model quasiperiodic. Okay, so I've just repeated this potential up at the top, and I'll draw a little phase diagram. But one thing I want to just point out is that by tuning the strength of the potential, one is effectively tuning the strength of the quasiperiodicity. And this allows for a direct comparison with random disorder, which can also be characterized by tuning the strength of the disordered potential. For quasiperiodic systems, at small values of the potential, the transport will be ballistic. So in other words, the mean square displacement of a particle initially placed at the corner of your system will scale as t squared. For intermediate values of V, so here between V critical 1 and V critical 2, we're in what's called the diffusive regime. And then finally, we can continue cranking up the potential strength, and eventually you'll see that your eigenstates will become localized. And now let's compare this to randomly disordered systems. And what we see is that in the presence of random impurities, we don't actually have any ballistic phase at all. For even finite amounts of disorder, the transport will be diffusive in nature. And then when you cross a V critical 2, it'll become Anderson localized. Great. Okay, so let's be maybe a tiny bit more precise about the nature of the eigenstates in quasiperiodic versus random disorder. Here, what I'm plotting is the inverse participation ratio, which is just a measure of the degree of localization of the state. And you can think about states as being either localized in real or momentum space. So here, dots that are red really correspond to states that are highly localized in momentum space, so extended in real space, while the blue dots represent states that are localized in real space. And a nice property of the Aubrey-Andre model that I'm studying is that it's self-dual upon Fourier transformation, which gives you this really nice symmetry across V is equal to 1. And by contrast, this randomly disordered system does not possess any sort of momentum localized states, even for very, very small amounts of disorder. Now I'm just going to take a line cut right around here in these plots. And just plot out the IPR to make things a bit more obvious. And we identify VC1 or V critical 1 as the critical value V that marks the transition from ballistic to diffusive physics in the quasiperiodic system. And that's this dashed line right here. And just, to really hammer this point home, in the randomly disordered case, this value V does not correspond to any change in the properties of the single particle eigenstates. Okay, so let's talk about the program for today. Our interest is in studying superconductivity. We'll start off by looking at the weak coupling behavior of the system, so studying the uniform static pairing susceptibility. And then subsequently, we're going to add in finite strength couplings, which allows us to determine the mean field transition temperatures in both quasiperiodic and randomly disordered systems for both S and P wave superconductivity. And then finally, I'll discuss a bit applications to experiment. Okay, we'll start off with this first bit here, which is discussing the static pairing susceptibility. And sort of the known classical result is that the susceptibility diverges logarithmically for a clean system as t goes to 0. This is the celebrated Cooper logarithm. Here I've written out the static pairing susceptibilities for S and P wave superconductivity. And what we're going to do is we're going to take these quantities and then project them onto their uniform component. And this is really the item of interest to us. Of course, one way to ask, what am I doing looking at the uniform component of the susceptibility when we would really expect that our solution to be quite spatially inhomogeneous. And my argument is that this quantity chi naught will nevertheless capture any divergences present in the actual susceptibility, so long as the actual susceptibility and this chi naught possess finite overlap. And it's actually a good thing to look at, because the performing the spatial average will neutralize spurious contributions from rare superconducting regions, as the overlap of the uniform solution chi naught with any localized solution goes to 0, as the system size gets to be very large. And what we're really interested in is how this quantity scales with temperature, or more accurately, the logarithm of the temperature. So if this d chi dt quantity saturates to a finite value, this signifies a weak coupling superconducting instability, the Cooper logarithm. And conversely, if this quantity goes to 0, there is no weak coupling instability. So first, let's consider what happens in the presence of random disorder for an S-wave superconductor. Here on the horizontal axis, I'm plotting the disorder potential strength, and this vertical axis is the uniform component of the susceptibility over logarithm of temperature. And again, so if this quantity saturates the finite value, there is a divergent Cooper logarithm. And as expected, we see that this S-wave superconductor in the presence of random impurities will remain superconducting even as the potential strength is cranked up. This is just what Anderson's theorem tells us. And conversely, a P-wave superconductor will be killed off by even very, very small amounts of random impurities, again, as expected. Now let's think about quasiperiodic systems. Here the results are very similar to the random case. I'm marking with a vertical dash line here the ballistic to diffusive transition for the quasiperiodic system. And as with random disorder, we see that quasiperiodicity does not suppress the superconductivity. And this bottom right quadrant here is truly the interesting result, which is that a P-wave superconductor in the presence of a quasiperiodic potential will remain superconducting all the way up to V critical 1, which is the point that marks the transition from ballistic to diffusive. And as we saw, by contrast, the weak coupling stability of a system with random impurities is killed off for any finite amount of disorder. One might ask, why did we choose to study P-wave instead of D-wave superconductivity? This is because our system does not have well-defined like C4 rotational symmetry, which means that there's actually no sharp distinction between S and D-wave superconductivity. But our system does possess inversion symmetry, which means that the P-wave, the channel is well-defined. But of course, you could study what amounts to D-wave superconductivity in the limit that the quasiperiodicity goes to 0. This is really just like nearest neighbor spin singlet pairing. And you end up with behavior that is entirely analogous to the P-wave case, which suggests that the presence of a weak coupling instability is robust to the exact form of the momentum dependence of the gap function.
Quick question.
Sorry, question?
Yeah.
Yeah.
Are we still working with the 1D Andre Aubry model?
Oh, no, this is all in 3 dimensions.
Well, this is in 3 dimensions, but
Yeah,
still
so all the
same.
results I've presented so far is in 3 dimensions.
Okay, even including the statement about duality and all that stuff.
Yes, yeah.
Okay.
Thank you. Great, okay, so we can return to our sketch from earlier and understand why the ballistic phase of the quasiperiodic system will remain logarithmically divergent at low temperature. And that's because if your eigenstates are localized in momentum space, so like in this red region right here, then scattering processes will be very rare. And as a result, you won't have the same sort of destructive interference that destroyed your Cooper instability in the case of random disorder. Great. Okay, so now we're going to move on to talking about systems with finite strength uplink, so we can be more quantitative about the transition temperature. So for this is the Hamiltonian that we'll be studying with interactions. For the S-wave channel, we set V naught to be attractive and V1 is equal to 0. And for P wave, we set V naught equal to 0 and V1 is attractive. We're going to treat the problem at a mean field level by using the following trial Hamiltonians and self-consistency equations. Is there a question? No? Okay. The mean field transition temperature can be identified by studying solutions of what is known as the linearized gap equation. So given an interaction matrix V right here, we can estimate the transition temperature by and finding the temperature at which its largest eigenvalue is equal to 1. So here are the results of that calculation as a function of quasiperiodic potential strength for both S wave and P wave. And we noticed something very strange, which is that the mean field TC seems to increase as the potential strength is increased. In other words, this is happening as the eigenstates are becoming more and more localized, which really doesn't make any sort of sense at all. This is really just a spurious effect. It's a rare region effect. And also finite size effect. And what happens here is that small localized regions, which are highly superconducting, will spuriously increase the transition temperature for finite size systems. So as a result, it's really more appropriate to think of this system as a granular superconductor composed of many superconducting islands that are all coupled to each other via weak Josephson coupling. And the corresponding resistance of the state will drop to 0 only when the islands become phase coherent, which sets another temperature scale for the problem, which I call TC theta. You can solve for this transition temperature by assuming that the only degrees of freedom in your problem are the phases on each island, which admits a description of the system as an XY model. And it's really the helicity modulus of the XY model that's equal to the superfluid density, which can be calculated numerically. And the onset of phase coherence in this model can occur at a temperature below the mean field linearized gap equation TC. And as a result, sort of like the true mean field transition temperature is taken to be the minimum of what these two approaches will give us. So here I'm plotting both of them on the same graph. And the actual estimate for your TC is taken by choosing the minimum of the linearized gap equation solution, which is shown in green, and the phase stiffness solution, which is shown in purple. As expected, we see that in the S-wave case, the TC is not significantly suppressed until we start to become quite localized in our eigenstates. But conversely, in this P-wave system, the suppression begins to set in right at V critical 1, which is I sort of like where there's this crossover between the amplitude appearing in these petals, controlling the TC versus the phase coherence being what sets the TC. And again, V critical 1 is what signals the transition between the ballistic to diffusive eigenstates of the quasiperiodic system. So to summarize, suppression of unconventional TC coincides with this ballistic to diffusive transition, which was the same sort of behavior that we observed in the original calculation that we did with looking at the uniform static pairing susceptibility. So now we can finally answer the question that we posed earlier, which is what is the analog of Anderson's theorem for quasiperiodic superconductors? And what we've shown is that quasiperiodicity really behaves quite unlike random disorder in the context of unconventional superconductivity. P-wave superconductivity turns out to be robust up to a finite critical value of the potential strength, which we don't note here, VC1, which corresponds to the ballistic to diffusive transition of the non-interacting model. And S-wave superconductivity conversely survives in all three phases, ballistic, diffusive, and localized. And finally, I'm just going to make a small comment about why this is relevant to experiment. we were motivated in part by the recent observation of superconductivity in twisted trilar graphene by Aviram Uri and collaborators for a range of parameters, really where quasiperiodicity seems to dominate the low energy physics. And if quasiperiodic systems behaved like regular disorder, then one would expect to not observe unconventional superconductivity in the stream, and that would sort of like tell us that it has to be, you know, conventional superconductivity. But as a result of these calculations here, we demonstrate that unconventional superconductivity is not ruled out in these Mori structures. If the quasiperiodicity is small enough, then it is possible that the substrate is still in a ballistic phase, and unconventional superconductivity is not suppressed. So further microscopic and transport experiments of the normal phase might help to sort of like further narrow the realm of possibilities down. And finally, I just wanted to thank my collaborators at Stanford, Trithip and Julian, and at Weizmann, also working with Erez and his student, Jiwan. And yeah, happy to take any questions.
Questions?
Yeah, I have a question. So if you take your quasi-periodic systems and add genuine disorder on top of that, I guess what happens to your results? Does it wash away?
That's actually exactly what we did to model the random disorder. Let me pull up. So this is the quasi-periodic system, and the way in which we modeled random disorder and produced all of the results is we specifically just added random disorder on top of it. So we selected these phases phi randomly.
I see. Thank you.
Yeah.
More questions? I actually have one. When you showed us the results on susceptibility and the weak coupling, S wave versus P wave. So P wave was not. I mean, right in the beginning, where P wave was not monotonic. Did you have with the amount of disorder? Did you like have an explanation for why this happens?
Sorry, is this the slide you're referring to?
But in the beginning, right in the beginning of the presentation, you had a plot of the susceptibility.
This is the only slide I have on susceptibility.
Right. So, okay. So I guess the S wave is not monotonic. Do we understand why that is? Or is it
You mean why it decreases a tiny bit?
Yeah. So in your lower plot, in the quasi-periodic case, it goes up and down.
Oh, this I think it's probably just numerical artifacts.
Oh, okay.
Yeah, because you can see that sort of we did a complicated averaging procedure in the supplement, and then the sort of the finite width of this line represents like error bars, and it seems like there's a bit more error for really low, because this purple corresponds to the lowest temperature we looked at, and it just seems like there's probably more error there in the numerics.
I see. Okay. And do you think there's anything specific about the Aubry-André model which is important for your results, or should we expect it to be generic?
I think the explanation for why we see the results seems to be tied just to the fact that you have your model has to have a ballistic phase, and B, the nature of rather the structure of the gap function in momentum space. Those are the two key ingredients here.
I have a question. So I think you studied the effect of the quasi-periodic perturbation on top of the regular periodic lattice. But instead, if you study the quasi-crystal itself and just apply the periodic Hamiltonian, do you think the result will change? Or
I guess so people have done this sort of thing, I believe, in one-dimensional systems. And there, I guess sort of there's no diffusive phase, I think. Yeah, there's so it's sort of I guess to answer your question, like this has been done, but not in like 2 or 3 dimensions. So I don't entirely know like what the results are, but I would expect them again to be similar so far as you have like a ballistic phase still present in this model that you're describing.
Could you say, just kind of repeat again, so in this, for the quasiperiodic model, we showed that the phase coherence temperature and the Tc extracted from linearizing the gap equation, they were perfectly on top of each other before the transition. Is that so? Could you? Yeah, so these two, the purple and the green curve, perfectly on top of each other before VC1 in the PVEF case?
No, so here it's actually, it's sort of hard to see, but actually the purple line goes straight up here.
I see.
Yeah, so it's not on top of it. Really, it's like VC1 is exactly where this crossover happens between like what is controlling the transition temperature.
Okay, so can you say how do we just understand this divergence of this purple curve basically?
I mean, it's not really a divergence. It's just sort of how I plotted this. Like, I mean, this obviously like, you know, has some finite value up here. It's just not shown.
Okay, if there are no.
And I guess sort of the answer, but like the answer to the question, like, you know, why you would expect the phase stiffness to be very high for small amounts of disorder is that, or sorry, quasi-periodicity. If I have very low quasi-periodicity, then the sort of the condensate is quite spatially homogeneous. I don't have a picture. It's in my supplement, but it ends up being quite spatially homogeneous. So then you don't really have this granular picture at all, and it's easy for your phases to be aligned.
I have a question. So it sounds like the message is that one might think the quasi-periodicity can hurt the unconventional here, I guess, P wave, but it doesn't. That's the message. Is that right?
Yes. Yeah. Or rather that quasicrystals are unique insofar as they have this ballistic phase.
Mhm.
And if you're still in the ballistic phase, then that won't hurt your superconductivity.
Mhm.
Mhm.
And S wave would be always fine, but the message is that P wave is also okay.
Yes, yeah. So really the message is all about the unconventional superconductivity.
Yeah. So the question is, according to how disorder would affect an unconventional superconductor, cuprates which are very dirty shouldn't be D wave, right? So you know about this story, or is this new to you?
I guess which aspect of this story? Like
the fact that disorder, I mean, if we go by this statement, that disorder would hurt unconventional superconductor.
Yeah.
Right?
Well, yeah, I guess, yeah, I mean, probably my, I mean, I'm not sure what you're about to say, but I guess my understanding of this is that, so really, like, Anderson's theorem only applies to, like, thinking about the weak coupling instability, but of course, you know, sort of like from a Landau-Ginzburg perspective, you can have, there's a transition temperature when like this product of like V times the static pairing susceptibilities of order 1, which admits, which I guess in a sense doesn't really care so much about like the behavior of the logarithmic divergence as t goes to 0.
So what I was going to ask is, what are are there examples where, you know, because of the Anderson's theorem, you do not expect unconventional superconductor, and otherwise maybe you would have. I mean, maybe what I'm trying to get at is what is the empirical evidence of Anderson's theorem being useful, which you are kind of rebutting here. But
yeah, empirical.
does that make sense? Does that question make sense to you?
Yeah, I think I see what you're saying, because it's a bit unintuitive that, or rather, like it seems like. Let me see.
I just want to know whether it's useful.
Yeah. So Anderson's theorem, I think it's in like the original paper that he wrote, it was all about S wave. So I think he was just trying to argue why
S wave superconductor can occur at all, right?
Sorry?
He was trying to argue why S wave can happen at all, right? Why S wave superconductivity can occur despite disorder. That's what he was trying to argue.
Yes, yeah, exactly. So his original paper was just about S wave, and people since then have sort of talked about the implications for like non-S wave superconductors. but yeah, I guess probably like my answer to this is that Anderson's theorem is probably not extraordinarily useful in practice, just because it's really only a statement about the weak coupling instability. So as T goes to 0, but if you have finite temperature and finite strength couplings, then there are other like explanations.
All right, any further questions? Yep.
Maybe a follow-up question. Are you suggesting that the superconductivity in TBG is S-ray?
No. I guess yeah, I'm not making any claims about superconductivity in these Mars systems. I guess really it's just the only statement I want to make is that from the perspective of Anderson's theorem, it is still possible for the superconductivity in these systems to be unconventional, so long as it's only weak quasiperiodicity.
I have a much simpler question. So just want to confirm the meaning of new C1. So that I understand that line separates the ballistic regime and the diffusive metal regime. Is it a sharp phase transition, or that's just sort of a crossover?
It's just a crossover.
It's a crossover. I see. Okay, Newton 1 is the self-dual point, so that's somewhat special. But Newton 0.5 isn't special. Like if I move the line to 0.55, I guess you could make the same set of statements.
Exactly. Yeah, there's definitely no sharp behavior occurring here. It's really just, this is the vicinity of where you start to lose the ballistic nature of your eigenstates.
Okay, thank you.
Any other questions?
I have one more. So how do you do calculations with quasiperiodicity? Maybe I missed the early part, so I didn't know. You probably answered this, but like, is this truly quasiperiodic, or is it like periodic with a very, very large commensurability?
Yeah, so specifically what we did is, first of all, we didn't want open boundary conditions, because if you consider a system with open boundaries, in a sense, you'll have scattering off of your boundaries, which then is basically disorder-like. So then that would mask any quasiperiodicity that we're trying to study. So what we did is we have an L by L by L cubic lattice that is has periodic boundary conditions, but within the like L by L by L square, it's not periodic. And it has this form for the potential.
How large can you go in your lattice?
The largest calculations I think were 30 by 30 by 30.
All right, if there are no other questions, let's thank Nicole again.
Yeah, thank you so much for attending. Appreciate it.